Exercise 11B, Antidifferentiation. And the end should be up here, just to make it look a little bit nicer. Today we are learning about antidifferentiating. What you need to be able to do is recognize the integration symbol or antidifferentiation, and then use the appropriate rule to antidifferentiate a polynomial or rational function. So even though we just completed an exercise that was all about finding area, what we're going to do is we are going to move towards finding the accurate area underneath the graph. But in order to be able to do that, we need to antidifferentiate. So the next couple of exercises are going to be about the theory, and then we're going to merge that together with being able to find the area. So that's the relevance to the previous exercise. Put 11A on hold, and we'll come back to it in a little bit. So what is antidifferentiation? Antidifferentiation is simply the process of undoing the derivative. So it is the opposite to differentiation. So usually what we have is an original function, and when we derive it, we go to the derivative function. So antidifferentiation is just literally the opposite. The difference is, though, we do notate it a little bit differently. So if I start with a particular function, we call it f of x. When I antiderive it, which is notated by this symbol, sigma, with respect to x, so that's what the dx stands for, we get the original function, capital F of x plus c. And I'll explain what the plus c is in a sec. But the notation is just a little bit different. So consider we're starting with a function, and then when we antiderive it, we go to capital F of x. But in either case, this is still a derivative, and this is the original, or the equation that is 1 degree up. The constant c means that you will find a family of many functions, which is what we're going to discuss now. So what does this plus c mean, and why do I need to add it on every time I antiderive it? So the example I'll say is, find the derivative of x squared plus 4. So when we antiderive that, we know that that is 2x. And then it says, get back to this function from its derivative. So how would I antiderive? And obviously we don't really quite know how to do that yet, but if you kind of think about the process of differentiation, what we do is we multiply by the power and we subtract 1. And if we're doing the opposite, then we just need to do these steps backwards. So instead of subtracting 1, what I'm going to do is I'm going to add 1 to the power, and then, this is a 1 at the moment, and then instead of multiplying by that original power, we're going to now divide by it. So 1 plus 1 is 2, so we're going to divide by 2. So what we end up with, the 2's cancel out, I get x squared. But obviously that's an issue. So I have antiderived it. I've done the opposite of deriving it, but what about this plus 4? How on earth am I meant to get that? So the whole purpose of this plus c is to account for the fact that there could be a constant, because obviously when we derive, that constant just goes, it cancels out. So when I antiderive, there could be a constant, I just don't know what it is. The reason for that is if we consider many of these functions. So if I have x squared plus 4, x squared minus 3, for example. If I were to graph each of these, so that's x squared plus 4, x squared minus 3, aside from the fact that my drawing is a bit crappy, what we can see is that all of these functions actually have the same gradient. They become steeper and shallower, they have a stationary point, all at the exact same x values. It's just that where the actual function sits is different. So that's the purpose of having a plus c. It's just to account for the fact that when I antiderive, I don't know what that constant is, so we always assume there's a constant. I mean, the c could be 0, but we always say plus c, and then usually the question has to give us a little bit of extra information in order to be able to account for that. So that is this plus c, and I'm trying to emphasize it because you must include it every time you antiderive, otherwise you won't get full marks. So in terms of the notation, we've already kind of discussed it, but we do have this integration or antidifferentiation symbol, and we always write with what variable we are deriving in terms of, because you could have a function, 2xy, but when you're doing it with respect to x, then you consider y as a constant in this case. Again, x squared plus c. So the way that I read this is the antiderivative of 2x with respect to x is equal to x squared plus c. And we can also call it the indefinite integral, which doesn't really make too much sense now until we get to the definite integral in a couple of exercises, but you can call it the indefinite integral. And so finally, we get to how do we do this? And it's very much exactly the same way that I just explained before. So when I derive, what I do is I multiply by the power and then I subtract 1. So doing the opposite, what we do is we add 1 to the power and then we divide by that original power. So what I mean by original is the power of the original function. So it's the 1 up. So that's why you divide by that new power. Just note that this process works as long as n is not equal to -1. So for example, 1 on x, this wouldn't work. And this one has its own particular thing that we do for it, and that'll be in the next exercise. Just a couple of basic properties of antidifferentiation. If I have a function that has a constant, so say I have 2x squared, for example, what I can do is I can pull that constant out and deal with the function, antiderive that, and then just multiply it. If it's a 2, it's generally not that big of a deal, but you can come across some more yucky constants, as we'll see in a bit, so this is quite useful. This one just says if you have multiple terms in a function, you can just antiderive them each separately, and then this one kind of just separates them all out, the constant and the multiple terms. We have already discussed notation, so feel free to read this slide, but that's what we've already discussed. And now we can finally get to some examples. So let's start with example A. Find the following antiderivative. What I can notice for part A is that this is a function that is within another function. So when we differentiate, we usually use a special rule, the chain rule. At this stage, we don't have anything like this, so the only way to be able to do this is to expand first. So you must expand. So for part A, I'm going to go ahead and expand. That's going to be x to the power of 4 minus 4x plus 4, and we're antidifferentiating with respect to dx. And now to antidifferentiate, as we mentioned, what we're going to do is we're going to add 1 to the power, and we divide by the new power. That's already a 1. Add 1 to the power, and divide by the new power. And here, if it's just a constant, we will just add an x, and of course, we never ever forget that plus c. So what does this end up looking like? So that's x to the power of 5 on 5 minus the 4 and 2 cancel out, so that'll be 2x squared plus 4x plus c. So this is the original function, and we'll have to get more information in order to find c. If you want to check that this is correct, just differentiate that and you should be able to get back to this original function, or the derivative function rather. Okay, so that's part A. Part B. This is an example of where pulling out the constant might actually help. So you can see that, we've got root x as our main function, but we've also got a root 2 in front, and I don't really want to deal with the root 2. So the first thing is I can rewrite this as 1 on root 2 times 1 on root x. Obviously, when I multiply, you just multiply across. So that can look like that. And then this is just a constant. So I can pull that out. So that'll be 1 on root 2, and then that'll be 1 on root x dx. And we can make that look a lot nicer by pulling the x to the top and changing the root to a -1/2. So we're going to go ahead now and antiderive. So I've just got a 1 on root 2 that's hanging on at the outside. That's multiplied by the antiderivative of x to the power of -1/2. So I'm going to add 1 to the power and then divide the whole function by that power. So -1/2 plus 1 is going to be +1/2. So that'll be x to the power of 1/2 divided by, and then the new power, as we just said, is 1/2 as well. So we've got a couple of things going on. The first thing I can see is that I've got a fraction divided by another fraction. So if you recall, when you have a fraction divided by another fraction, I'll just do it the long way, but just so that you remember how to do it. When you do your keep, change, flip, so you keep the first one, change the sign, and then flip this. So you can see that what is actually happening is that this flips and multiplies there. So it'll be 2 on root 2. So we'll have a 2 on root 2, and then the x to the power of 1/2. I'm just going to write that as root x. You can leave it there at that point, or you can rationalize the denominator just to make it look a little bit nicer. And also, sorry, you might have picked up my mistake, but we should have included a plus c. Always include that plus c. And it is very easy to forget. I still do it till now, and it's something that, if you do see it, pick up on it. Okay, so we're going to multiply both the top and the bottom by root 2, so I'll end up with 2 root 2, and then because they're both x's, I can just put that underneath the same square root, and then root 2 times root 2 is 2, and then the 2's can cancel out, so I just end up with so that's plus c, equals root 2x plus c. There are obviously multiple ways to do this. If you wanted to keep the 1 on root 2, sorry, on the inside, you can, but for me, I just don't want to deal with square roots, so I'm cool to just pull it out on the outside. Okay, C. Here we can see a function divided by a function. Again, when we derive it, we use the quotient rule. There's no such rule for now that looks like this for antidifferentiation. So again, you need to separate it out. So we cannot have a function divided by another function. So what I'm going to do to separate it is I'm going to write each term over its denominator. And then I'm going to go ahead and simplify. So I've got 2x's on the top, cancels out with 3 at the bottom, leaves only 1. 1x here cancels out with the bottom, that leaves 2, and then the last one doesn't leave anything. There's nothing to cancel out. So what that leaves us is I'm going to take the x to the negative to the top. I've then got a 2, x to the power of negative 2, and then x to the power of negative 3 dx. Now, I can go ahead and anti-differentiate it. If you recall, I said you can't use this rule where you have it as power of negative 1. And the reason is if I were to add 1, then I end up with x to the power of 0 and it cancels out. And that doesn't quite make sense. So we will come back to this one later on. But actually, what 1 to the 1 on x or x to the power of negative 1, the antiderivative of it is log ex. Now, the rest is all quite straightforward. So add 1 to the power, divide by that power. Add 1 to the power, I'm going to make it a negative 2, add 1 to that, and then divide by that new power. And of course, we have our lovely plus c. All right, just want to kind of simplify this just to make it look a little bit nicer. So that'll be log ex. Now, negative, negative cancels out, so that'll be 2, and I'm going to take the x to the bottom. And then here, if I want to take the x squared to the bottom, I've got also a negative 2 there, so that'll be negative, I can write it as a half, or rather, just 1 on 2x squared and plus c. So that's it for part C. Okay, for our final one, D. Again, here I've got a function multiplied by another function, and it's also at the bottom. So there's quite a lot going on, and we want to simplify it before we start working with it. One way to think about this denominator is that that's x to the power of 1 times x to the power of a half. And we know when we multiply two indices with the same base, we just add the powers. So that's x to the power of 3 on 2. And of course, because it's at the bottom, then it's going to be x to the power of negative 3 on 2 when I take it to the top. So that's all I have to do in terms of rewriting it. So that'll be 2 x to the power of negative 3 on 2 dx. You can take the 2 out, but it's an easy enough number. So add 1 to the power. So that'll be negative a half, divide by that new power. If you remember, when I'm dividing by a fraction, all that happens is that fraction flips. So I'll end up with 2 times 2, which will be negative 4. And I can take that x to the negative half to the bottom. So that'll be negative 4 root x. Of course, I do it a lot. I forget that plus c. So please don't forget it. Okay. Now we move on to this example, and in this example, we have finally where we do find that plus c. So you'll generally see that we'll have this phrase here. It passes through a particular point. Now the purpose that we have this is that at the end, once we've anti-derived it, we can substitute that point, and then we can find plus c. So a curve with this equation, y equals f of x, passes through that point, and its derivative f dash of x is equal to that. Find f of x. So I have the derivative. I want to get back to the original. All I have to do is anti-derive that. I'm going to straight away take this to the top just to make it a bit easier. And then I'm going to go ahead and anti-derive that. So add 1 to the power, divide by the new power. Add 1 to the power, divide 1 by the new power, and don't forget that plus c. Simplify this, so the 3's cancel out, so that'll be nice. The negatives cancel out, and I'm just going to take the x to the bottom plus c. So that's what I end up with. That's what my f of x is equal to. But of course, I have a little bit of extra information, which is going to help me find that plus c. So when f of x is 0, then y would be, when f of x is 0, then x is 2. So I'm just going to sub that straight in. So I get 0 equals 8 plus a half plus c. The way to work this out, 2 times 8 is 16, plus 1 is 17. So I have 17 on 2 plus c. Therefore, c is going to be negative 17 on 2. And I can write my final equation as x cubed plus 1 on x minus 17 on 2. And that's it for this exercise. So please go ahead and complete the questions and practice your antidifferentiation. See you later.